between. No, consciously plan.
Oh, okay.
No, this is clearly.
So nationalistic. Okay, welcome to the morning session and the last academic session of this meeting. And today our first speaker is Apoorva Khare from Indian Institute of Science and Analysis and Probability Research Group. And he will talk on probability inequalities on metric, not groups, but semigroups.
Thank you very much to the organizers and whoever else thought of bringing me here to the probability conference, since I'm not really a probabilist. So anyway, this is about, as the title says, it's about some basic stochastic inequalities, which one is used to seeing over, say, real value random variables or Rn value random variables. Now for and even beyond Banach spaces, something like metric settings. So that I'll talk in two different settings, and we will see how time.
So I will maybe 5 minutes before.
Thank you. So yeah, so I don't need to tell anybody about the Bible of Banach space value probability, and so here is one result. For example, suppose xn are independent random variables, and you write down there's some converges almost surely to x if and only if it converges in probability. This clearly only needs the notion of plus and convergence. So one can easily ask, does it hold more generally than Banach space value? And yes, this was shown over any complete metric group in the 1960s, quite a long time ago. Sorry. So one can ask, does it hold even more generally than groups? And I will explain why the answer is true.
L0.
Sorry, what?
L0.
Just random variables. Since I'm not the probabilist, I will use notation which probabilists don't understand. So please forgive me for that. But as far as I'm somewhere I have read L0 also. I think maybe Dudley's book also. Dudley's book or somewhere is there. Okay. So yeah, as I said, in this talk we will consider both primitive settings and Banach spaces. So and these are obviously not just like these are sort of very well considered. Obviously, finitely generated groups. This is for just shuffling cards on permutation groups. Parthasarthi, in whose honor there are these recent volumes coming up, which I think most of the audience is aware of. Yeah, he had his first book, actually, metric space. And people, of course, look at the groups, the manifolds, and manifold learning, and this and that. So, okay, so here is an example. If xn goes to, so what do I mean by we will study these inequalities in primitive settings? What do I mean by primitive? I mean that if xn goes to x almost surely, then it goes to x in probability. This fact, whether one studies it in B-stat first year, like or second year, B3, like we did with real value variables, or more generally, it requires very little to state the fact. It only requires convergence. Actually, that's it. And some sigma field or something. Right? So sigma algebra for random variables, but only convergence. So you can state it for xn and x, taking values in a metric space. The nice thing is you can prove it in this very basic, extremely primitive setting. You can prove it in the most general setting you need to state it. So this is what I said I read in Dudley's book. Yeah. And so what we were studying was sums of independent random variables of the kind is in the theorem I stated at the beginning, there is equivalence. And then instead of, so the modern trend, instead of looking at exact convergence, you try to improve on the PN behavior. So now what do you need to state such an operation in the spirit of the previous discussion? You only need a group operation, which is binary and associative. Actually, group is a misnomer. You just need a binary associative operation. You don't need an inverse. And you need a distance function. So we worked in a metric semigroup with a binary. So, when I say we, it's not the royal pronoun. This part was joined with Bala Rajaratnam. He is a probabilist and statistician. He was at Stanford when we overlapped, and then he has since moved to Davis, and I moved to India. And so one can define a semigroup with a bi-invariant metric, or one can define a semigroup with just a left-invariant metric, or just a right-invariant metric. So, for example, I think that compact Lie groups have bi-invariant metrics. You sort of just average out that hard measure. Whereas all Lie groups have left-invariant metrics or right-invariant. And in group theory, so yeah, so unlike like say the like probability operator semigroups, you don't have an identity semigroup. That is a monoid. Semigroups with identity are called monoid, as A.R. Rao taught us in the stat first year. Maybe on the first day. Monoid semigroup. So yeah. So I will stick to semigroups without identity, and I will talk about monoids when I need to talk about monoids.
So, one question.
Yes.
For any separable matrix space, is that in the predicate setting?
Yes. It's in text. It's in Dudley's book.
Okay. So, as long
In
as
metric space, but separable metric space.
separable is needed.
I'm putting it in. I don't know. So, maybe it's not needed. Maybe it is. Okay, so bi-invariant semigroup, metric semigroups, of course, include Banach spaces and so on. It includes all the discrete groups. It includes compact groups. But they are semigroups, so you can do more. How to deal with lack of identity? Use the bi-invariant. So if you have distance from AG to AH, I want to show it's independent of yeah. Okay, but you use the bi-invariant. This is not, I will tell you what I want to use it for now. So if you want to talk about something like this, right? Then, of course, what is the norm of some vector? It's the distance to the origin, so the distance to the identity. So if the semigroup has an identity, if it is a monoid or a group, then this is fine. Otherwise, what do you do? Well, then we say that if you to deal with the lack of an identity, we define it to be the distance from Z0. Take any element Z0, and then just put on both sides, either on the left or on the right, doesn't matter. And the claim is this is independent of Z0. So this is why you need the bi-invariance, the metric, and this is the key property. Even without an identity, this distance is independent of Z0, as the simple calculation shows. So here you start with this, then you write down multiply on the right. So you multiply on the right by G, so you get Z0 G, Z0 G squared, and now you can remove on the left because you could go from the third term to the second. And so you see that the left-hand side depends, supposedly depends on Z0, but the last expression doesn't.
So you need both the invariants.
But you need both of them. So not just left invariants. And the sort of the sad thing in some sense that you gain this kind of independence even without the identity. What you lose is sort of the lack of generality. For example, as I said, bi-invariant metric semigroups are very, very few, say that among the groups, whereas every single D group has a left invariant. So asking for just left invariance or just right invariance is much more general than bi-invariance, even among say very prominent groups like random matrix theory or geometry. The nice thing that I noticed, sort of, we noticed, this time it's the I noticed, avoid me. More recently is that the only use of this right invariance is to make this property. So rather than ask for right invariance, one can ask for this property. And as long as z distance from as long as the first term equals the third term, regardless of how I get there, if I can just ask for the property that the first term is independent of G, and therefore equals the third term, because you can put z not equals G. That's good enough to avoid using right invariance, and therefore the setting can be generalized faster. Okay, so now to get to the which inequalities I'm talking about. So this is the one I will mainly consider in this talk. If there is time, I will talk about something else. So this bounds the sum of independent random variables, taking values in Banach spaces. It was proved by there was Kahan and then Hoffman-Jorgensen. It's named after Hoffman-Jorgensen. And this is the inequality from the Bible, let's say. So suppose to be the separable Banach space. We look at random variables which are independent, and then you can bound some. You can talk about something. Look at the biggest possible magnitude of the partial sum, and then you can do something like that. Okay, fine. So this is the inequality. There was another inequality 10 years later for similar flavor. The same notation, but then they generalized it to just not 3t plus s, but even number times t plus one number less plus odd, plus some number times s. And it was of a very different flavor in appearance. The last term was the same. No. This term was slightly different. Not same. So both versions again require the question that we were looking at, Bala and I, Bala Rajaratnam, where we were looking at how more primitive can one make the set. That was the primary motivation. So they require only a distance function and a semi-group operation. So certainly we can do it here. The other thing was it is not clear if they have a common generalization. They, both the constants look sufficiently different, the dependents look sufficiently different that it's not clear if they have this common generalization. Of course, there is something in the numerator that's the same. So what about the rest? So the next result that Bala and I proved, and it achieves three objectives. It strictly strengthens both of those results, even including in the real value. Simplest case of R values random variables, even that got strengthened. It unifies that version, the version I stated above, and some other versions, or at least special cases of these versions. And finally, it is stated and proved in that primitive set. So the idea was to sort of achieve multiple things at once, and I just state the result. It's very technical. So if it's going to generalize both of those and they look so different, it's going to look even more weird. So again, just to set the notation, define UM to be the max of these guys, the distance from, and here I can vary Z1. That's not, that doesn't technically turn out to be too bad. So that's already something that was not done in the original Jordan's inequalities. You fix two elements Z0 and Z1 and don't write distance Z0 to Z0 10. That is the convention for the norm, the substitute for the norm. And it's independent of Z0. No, you put Z1 as well, and that still works out fine. And then define, define some set of indices for which the random, these UMs behave somewhat nicely. I'm not even going to get into the technicalities, so don't even ask me what this means. Now, here is the statement. It looks sort of horrendous, but it turns out to generalize. But the point is, this is exactly the same. And the left-hand side is sort of something along the same expression. UM bigger than some big number times. In the expressions, there was one T1 and there was S. Some number times T1 plus some number times S. Here we can do many, many others. So there's NITI together. This kind of a formulation might have been due to Montgomery Smith and Dichenko, but I'm not sure. I don't know. This part is the stuff that generalizes it. There is some pure numerator terms and there are some numerator and denominator terms with the value. So, with a judicious choice of various parameters, you can specialize to both inequalities. This part, as I said, is exactly the same. The probability that the max of the norm XJ is Z0 and Z0, bigger than S. Okay, so moving on, shall we say. So this combines, we have to do a lot of jugglery to obviously make all these things work together. It works out. It's not a long paper. We also strengthen this paper, result in the following sense that instead of working with these ideas, one can work with the order statistics. And this is not our idea. This was an idea due to Rudelson. And he suggested it to these guys, and they actually showed this result of Banach spaces, which we then improved and subsumed other stuff. So this, so the goal, maybe the upshot of this is that yes, there are fundamental stochastic inequalities which even now admit, like unifications, not just generalization, but unifications across variants which were not known in the literature. Okay, here's one. So a couple of applications. One is that it implies several bound results for tail sums using this theory of decreasing variance. This is again something very technical, which we looked at previous papers, and I'm not a probabilist. So Bala said you should study some probability, and so I looked at some stuff and we wrote something together. A more recent version was due to Bhagyan and Don Richards, who looked at random walks on the cone on the positive definite cone. Okay, and that is as you are here in the lambda Bhatia, so you know about the Riemannian metric and the matrix geometric mean and so on and so forth. So that manifold. And they looked at orthogonally bi-invariant, I should have mentioned bi-invariant distribution. So there is the orthogonal group is a Lie group, but it's compactly group. In fact, we talk about bi-invariant distributions, and one can do it. But however, as I said, bi-invariance is a strong hypothesis. Even among Lie groups, it's very restrictive. So how about can one extend this to all Lie groups, such as ones you see probability as well? And that is the second part of the talk, which is this. So metric bi-invariance is not needed. What is needed is that P property. So let me call the semigroup with the left invariant metric, because you see I have only the left translation by Z0. The problem is I don't have an identity element. That's why semigroup I can't write down Z0. I can't cancel Z0 and say it's E to G because I don't have an identity. So a semigroup with a left-invariant metric is strongly left-invariant if this key property holds. And the idea is that this is a reasonable substitute for right invariance. You don't need right invariance if this property holds. And at the end of the talk, I'm going to tell you that this is really the same thing as something else, which is much easier to imagine. I mean, this isn't hard to imagine either. This property, left translation without identity doesn't change the distance. But it's even easier. Maybe I'll tell you the punchline. The point is that this property is equivalent to having an identity. Once you have an identity, you can obviously cancel and say this is the distance from E to G if you have an identity. But the problem is what if you don't? Well, if you don't, then in general, a metric semigroup need not embed into a metric monoid as an identity. But if this property happens, then it necessarily embeds in a metric monoid. The converse is obvious. In any metric monoid, this is you cancel that. So that's the punchline of the talk, just to tell you. But anyway, so example, every bi-invariant metric semigroup has this. This is independent of Z0. We did the calculation without using identity. Every left-invariant metric monoid, i.e. with the identity, but without right invariance, is also an example. So we have two competing examples. One has right invariance but no identity, it satisfies the property. One has identity but no right invariance, and that satisfies the property. You can naturally ask which one is more general. We will answer that. Is one of them more general? If so, which one? We will answer that. And in particular, now because of this concept or this example, every single D group now can be that falls under this paradigm. So what I want to say next is that all these Hoffman-Jorgensen inequality and other such stuff do come under do get satisfied in this condition. And this appeared just last month in the KRP volume. Yeah, so first volume, I guess. The above general form of the Hoffman-Jorgensen, including the order statistic strength, and it holds over every single strongly left or right invariant metric. So in particular, it holds over every D. So similarly, there are other things. Ottaviani score inequality, Bogulski's minimal maximal inequalities, Levy, Ottaviani, I think. There are a bunch of other inequalities which I mentioned in the paper, which also therefore go on from not just bi-invariant metric semigroups, but over every strongly left or right invariant semigroup. In particular, these inequalities hold over every D. As I said, I tried to look around, but to my knowledge, I couldn't find these things recorded over every D group in the demo. Okay, so oh, sorry, I seem to sorry. So yeah, please. We started, etc. Okay, so the next few slides then concern the setting. As I said, holds over every legal. So there are two competing settings. We are both examples of this. One has left invariance. Sorry, one has identity but no right invariance. One has right invariance but no identity. Which of these is more? So first of all, the claim is that this one is less general. The left invariant metric monoid is more. All you want to do is ask. So basically, this has identity, but no right invariance. This is right invariance, and we claim that then you can automatically put an identity. You can attach an identity. There's this thing in I think even a ring. You can talk about a ring without a one. I think people call it like RNG without the I identity. But then you can formally attach a one to the ring in some sense, at least to an algebra. Over the field, you attach a one-dimensional vector space, call it the. The same thing can be done in a metric semigroup, which has bi-invariant. So every bi-invariant semigroup is either a monoid, it already has an identity, or it is a set of, it is the monoid minus the identity, meaning it has exactly 0 or 1 element less than a monoid. And what is that monoid? Just we look at idempotent. If that G has an idempotent, then why don't I write this down? So if you have a G equals G square, then the distance from G to GH. What is this distance from G square to G square H? What am I doing now? This is where I should not be doing stuff like that. You immediately. Oh, sorry. What am I doing? I'm trying to do. Oh, this is the. G is the identity. So I should say distance from H to HG. This is the distance from HG to HG square. I can multiply, right? And now, but HG to HG, G square is G. So this is the distance from HG to HG. And if a metric is 0, then this is using the right invariance and similarly left invariance for the left. So it's a two-sided, I think. G is a two-sided. Okay, good. At least I can prove something. Okay, so G is exactly 0 or 1. So if you have any idempotent in the bi-invariant semigroup, it has to be the identity. If there is no such idempotent, you attach one and you define this to be exactly that, and that works out. So certainly these guys are less general. The left invariant metric monoids are more general because every one of the latter embeds in the form. Now, what about strongly left invariant metrics? Where does that fit into all this hierarchy? There's left invariant semigroups. So yeah, so there's strongly left invariant semigroups. These are all the left invariant metric monoids. These contain meaning you can embed the bi-invariant. And then there are metric groups. So while the strong left invariance is crucial, it might be that it is not needed. Maybe the mathematics is just like convenient, but you can actually prove that without the word strong. So this semigroup means without identity. Strongly is that the distance from Z0 to Z0 G independent Z0 for G and Z. Maybe this is following from the consequences. It sounds impossible to me. It sounds impossible. And if it doesn't follow, then at least can one classify which left invariant G? I give you a semigroup, which is left invariant metric, and no identity. When can it embed into a metric monoid? And so here is the answer. Indeed, those two notions are not the same. So strongly is necessary. There are left invariant. So there exists a metric semigroup with two generators. G is countable and discrete. So it's of course complete. And it is left invariant metric, not right invariant, left invariant metric, but it is not strongly left. And in particular, then it cannot embed into any left invariant monoid. Because if it did, then those are already strongly left. So it cannot, when I say embed, by the way, embed means embed in both the senses, embeds as a group, embeds as a semigroup, embeds as a metric. So it embeds isometrically and homomorphically, and that cannot happen. You cannot identify, there exists at least one such semigroup, which I had to literally construct by hand and make it work. But yes, it can happen. And secondly, a left invariant metric semigroup embeds in this monoid if and only the distance, the metric is strongly left. So certainly, if it is strongly left invariant, it embeds into a if it's the monoid, then this metric is strongly left invariant. Because you can just cancel the Z0 and write E common. But the converse is true as well. If it embeds and it isn't already a monoid, if the idempotent doesn't exist, you can attach one and make things work out. Okay. So basically, the punchline, as I said, therefore, is all the results above equivalently hold over left invariant. Okay. Is there any time for changes or can I go on?
Yeah, 5 more minutes.
5 more questions. Okay. Yeah, so in particular, therefore, these results equivalently, I said they hold over all strongly left invariant semigroups, on the Ottavriani and Boguski and so on. They just hold over left invariant monoids. In particular, if you have a group like a Z group with a left invariant metric, then all of those results hold over those. Okay, maybe I will change this. Fine. So since I have 5 minutes, I will tell you this other thing in the 5 minutes. So that was one inequality, the Hoffman-Jorgensen sum. Now, completely switching tracks, we looked at abelian groups now. We looked at groups and in fact abelian groups. And in that there is another fundamental inequality from the 1960s, again by Tahan, which compares the LP and LQ norms of Rademacher sums. heard about Rademacher variables from Patsuri yesterday. So yeah, so again, for all there exists a universal constant given any P and Q, such that for all Banach spaces, all finite set of vectors and independent random vector variables, the Q norm can be bounded by the P norm. For a fixed P and Q, you have this constant. And if you have P between, so if you have P is 1 and Q less than 2, then some constant is obtained. There are, of course, many additional results and so on. So again, what is the primitive structure to state it? Can one prove it in that primitive structure or some sharp, less sharp variant, and can one recover the optimal bound? So the answer is yes. So what is the primitive structure? You need to add, because these can independently plus minus. So we better have this, first of all, minus means we need a group. Talk about symmetric variables and so on. So ideally they are abelian. It doesn't order, you add in something. So there exists a universal constant again if you fix P and Q, depending only on Q and whether Q is bigger than P. This is also the case in the previous one. It's not very clear. Such that for all choices of separable metric groups, finite sequence value, G value vector, and the sectors and different markers. You have this. This is the Q norm, the 0, 2 or this thing. But the Q norm is not to the summation of these there. It's to a multiple. So that was sort of necessary to tweak the proofs. And again, this inequality was not the point of what I tell you. It was the fact that led from this inequality. And then in particular, one may choose some large constant like this. If G is norm, and by norm I just haven't tell you what I mean, then the stronger statement. The stronger statement that we had in Banach spaces, you get the better one. You don't have all these factors, you get the simpler and better one. And what is norm? Norm is exactly what you would expect from a norm, which is that the distance from 0 to G, so rescaling of vector G, is that scalar multiple times the distance to G. But in the difference between vector spaces over R and groups, is over R I can take root 2 times the vector. In groups I can only take 2 times the vector. 3 times G square, G cube. I can't talk about non-infinite times. So that's the definition. So this I will probably skip. So I'll just end with the last thing, which is a nicer story, guys. So if the group is abelian and not, what Bala, this is again joint work with Bala Rajaratnam. What we proved is it embeds into a Banach space, and that's why one can make it. That is exactly why we recover the sharp constants. Because if you work with variables in if we say that you work with G value variables, then if G is embedding in the Banach space, then you work with B value variables. And with Banach space value variables, you of course get back the norms for Banach. So the trick was not to prove so I think in this paper we started by mentioning that the proof in the in whatever this theorem, the proof for Banach spaces here goes through verbatim if you look at non-abelian groups. But then we said that the conceptual reason why the proof goes through is because every non-abelian group is sitting inside a Banach space. So of course the G-value variable is a B-value, and therefore it's not. So then, but then now because of this Hoffman-Jorgensen, it was obvious that the natural question is, can one extend it to non-abelian groups? Maybe you have semigroups, maybe not, but maybe you can do something in the spirit of Hoffman-Jorgensen. Although technically you use symmetric variables and Rademacher sums, but can one do something like that? Then it turns out that, first of all, something nice happens. If a G is a non-metric group, so there's a norm, the metric is a norm, and the metric is left-invariant, then the metric is automatically right-invariant. So really we get that this symmetric sums, the group is not abelian a priori, but the metric is binary. Okay. So then one can ask, so abelian norm groups are of course, every Banach space is an abelian group with a norm. The rescaling scales the norm. But what about non-abelian? And then there are versions, there are these old results that prove that you cannot have non-abelian non-metric groups in certain cases. Nilpotent groups can't be a norm, connected Lie groups cannot be norm except Rn. But on the other hand, if you have a monoid, as we discussed monoids, such a norm always exists. So the question was, what about norms? And then this is the story that I think I mentioned here in the talk in January. this is the last slide after this. I emailed lots of people. Nobody told me an example of a non-abelian norm group. Nobody said that such groups cannot exist. So it has to be one or the other. Which one is it? And then I was visiting Tao, and then we started discussing strategy and blah 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 blah. This is not, I'm not going to tell this stuff, right? But the answer is yes. There is no non-abelian norm group. So the theorem is that if G is a group, then G has a norm. If and only if G is abelian and torsion free. If and only if G is basically a subgroup of a Banach space. So the same. So basically, the Banach spaces and their additive subgroups with the inherent norm, the inherited norm, are the only examples of groups with norms. In particular, the Kinchin-Kahan inequality does not have a generalization to non-abelian settings because such groups don't exist. And the proof actually involved a Chernoff problem here. I don't see it here. So yeah, it was all started with this project was motivated by the probability question. It ended up being solved by probability methods. Okay, well, many happy returns, Rahul. And I can, if you have some free time afterwards, I can have suggestions of how to use your free time. These are this one with Bala, and this last one which extends the Hoffman surface, and the middle ones are with the teaching. Okay, thank you.
So we have time. We have time for one or two questions.
So one thing I wanted to ask, so let's move on to the first version of Hoffman-Jordan's inequality. Okay. So probably the proof that is given in Talagrand and Bengaluru, the same one will also work for, because I just worked it out a bit, the same one will also work for bi-invariant vertex semigroups.
Probably.
The same argument.
But as I said, we also wanted to extend the other ones. So yeah, I don't remember. I started out not with that group. I started out with the one for Hitchenko and Montgomery. That is like in 5 or 6 steps with some counting, various stopping times and counting arguments and re-indexing summations of all kinds. So that seemed the more technically difficult one to subsume in the more unified version. So I started with that proof and made it work. But as far as the first variant alone goes, probably you will have to check it. Maybe you check it.
I checked it out last night.
Okay. Good. I'm glad it works. Thank you. It just uses that. So even they knew, I guess, but they were writing a book on Banach spaces, so they figured why.
Someone is doing advanced homework.
They should have had a homework problem.
Yeah.
Apoorva, thanks for the very nice talk. Now, what I was wondering is a very nice generalization. Puts a lot of things under a big umbrella.
Yes.
Has it given anything new?
So this is what I've said. So far, I don't know. Again, that's your job, not mine. But one thing I will tell you is this: it happened last year. There was a paper that came out last year, not by me or Bala or anybody. This one. So there is a start. So
Some new tail bounds.
I assume so. Yeah, on the for random box on PD. So I expect that now that it applies to all Lie groups. That was not when they did it. I had not written the paper, so they only applied to bi-invariant because orthogonally bi-invariant. Orthogonal group is compact; it doesn't metric. Now, I of course, the moment I proved this, I put the preprint. I told them that now you can apply it to all the groups if you want to do something. But yeah, so now one has groups that get used in RMT and other cases. So maybe, but yeah, at least there is one thing that has already. There is a start.
Thank you.
Okay, let's thank Apoorva again. So the next speaker is Arijit Chakrabarty from ISI Kolkata, and he will talk about clustering of rare events.
Thank you, Rahul. So we are here to, celebrate Rahul's whatever Rahul's B-Day. But the point is, I had a story, but I actually in store because there's something after this. Okay, so the title of my talk is Clustering of Rare Events, and it's a joint work with the Gandhi University. It's based on a couple of papers. The broad question that we started with is, if a system deviates from its usual behavior, how likely it is to cause a cascade of additional deviations? How likely is the deviation to persist? So just to fix ideas, start with a stationary process with finite mean mu, and given a fixed threshold epsilon, which is positive, suppose that the sample mean is larger than the population mean by at least epsilon. Now, if you were under very loose assumptions like ergodicity, okay, this will go to mu, right? So probability of this goes to 0. So this is already a rare event. The question is, if this rare event occurs, how likely does it make the subsequent rare events? Okay. So what I mean by subsequent rare events, you still ask the same question: sample mean larger than population mean plus epsilon, but now it's a sample of size n starting from the j observation. So in other words, I'm looking at close events. Okay, so this is a rare event that has occurred. How likely are the subsequent events? We'll make this question more precise in the next few slides. So just to, I'm sure everybody here is aware of Kramer's theorem. So Kramer's theorem says that on the logarithmic scale, it's like negative lambda star, x by lambda star is nothing but the Fenchel-Legendre transform of the log homogeneity. So Kramer's theorem gave the exact trait on the logarithmic scale. So in other words, this is like e to the power negative n lambda star. This was proved by Bahadur and Rangarao. So what they showed is this probability is actually e to the power negative n lambda star times a polynomial correction. Okay, and they also exactly calculated the constant. So in other words, this is called strong large deviations because this is a stronger result than that of Kramer. Stronger under additional assumptions though, because if you take a log and divide by n, you get that. Okay, so this actually gives the rate. So just like in one direction, Bahadur and Rangarao generalized Kramer. In another direction, Gartner and Ellis, they generalized the result in the sense that they studied sums of independent, from their result, you can derive large deviations for sums of independent random variables, which are not necessarily identically distributed. Yeah, but again, that's only on the logarithmic scale. The square was completed by Shaganti and Setu Raman in the sense that they studied strong large deviations of sums of independent random variables which are not necessarily identically distributed. So in my lingo, strong large deviations means when you get the exact trait, whereas large deviations means on logarithmic scale. That's the language I'm using for this talk. And I'll tell you why. Because what we looked at is, given a rare event occurs, the conditional probability of the subsequent events. So you need to look at the ratio. Okay? And for the ratio, you need strong large deviations, like I said. Just understanding the logarithmic rate is not good enough. Which is why I'll refer them as strong large deviations. Now let me quickly go over the folklore. So if Zn is the sum, since this is the folklore, I'll not make it very precise. It's folklore. So Zn is sum of several independent random variables. Then if you subtract the mean, then any deviation of the order of the variance is usually called a large deviation. Okay? Whereas a deviation which is much larger than the standard deviation but much smaller than the variance is usually called a moderate deviation. And there's a qualitative difference between large deviations and moderate deviations, which is that large deviations depend on the entire distribution, like in Kramer's theorem. It depends on the log Fenton-Legendre transform of the log momentative function. Whereas moderate deviation depends only on the variance. So I mean, again, this is just a folklore, so I'm not making things very precise. But the idea is, if you divide by the standard deviation, then some kind of Lindeberg central limit theorem will tell you that it has a Gaussian limit. So if eta n is much larger than the standard deviation, then this probability will go to 0. So, but of course, I mean, there's a caveat that this loose idea of large deviations and moderate deviations don't always hold. I mean, this in particular, whatever I have written here, this is true usually, but there are situations where this fails. So, but in this talk, whatever I'll talk about falls under this umbrella. So that the caveat is not very important for this.
Assume the variance closer then.
Yes. So these things are all under the carpet. I mean, Z is the sum of several independent random variables. The number of summands increase and variance goes to infinity. So in other words, we are in a situation where Lindeberg central limit theorem, this hypothetical. Of course, I mean, for these two hold, you need much stronger assumptions. Okay, so now the setting of our work. So let Xn be a stationary ergodic process with finite exponential moments, and I call Ej epsilon n the event that the sample mean of the sample of size n starting from the jth observation exceeds the population mean by epsilon. So that's exactly what I said. Words. The sample of these many observations deviates from the, well, not deviates and exceeds the population mean by at least epsilon. So this is the question we have in mind, that if mean of the sample of first n observation exceeds by epsilon. So now, regardless of whether I'm trying to make the question precise. Regardless of whether this occurs or not, the moment you have this is positive, just by arbitrarity, you will get that this goes to infinity, because if you scale, if you look at the partial sum and scale by 1, that goes to something, right? That goes to something positive. So just by asking how many of them occur doesn't make sense. We have to look at the nearby ones. Okay, the nearby gates, that means J0, 1, 2, etc. And how many of the nearby ones occur, that depends on the memory of the process. So of course, I haven't yet told you what I mean by memory. So memory of a process is best understood in the context of Gaussian processes. A stationary Gaussian process has short memory and the sum of the covariance. Before that, let me quickly tell you why. I mean, there are several reasons why this is taken as a standard definition of short memory. Because in this regime, it resembles the IID random IID. For example, if you look at the variance of partial sum of x0 to xn, that grows like n. And the same happens over here. The growth rate of the variance is same as that in the IID case. And there are several other reasons for which this is taken as a short memory in the context of Gaussian process. Whereas it's called long memory if something like this happens. I mean, this clearly shows that the covariances are not summed. Now, this is the definition for a Gaussian process. We work in a setting which goes beyond Gaussian. We work in this thing of moving average process. Our have a collection of IID zero mean random variables with finite exponential moments, and we look at a collection of coefficients such that we are square summable, and we construct a mean mu moving average process in this way. The moment age is finite, this sum makes perfect sense, because these are finite variables. Follows from there. So then we'll call xn to be a moving average process with these as inputs and mean mu. So now the model is now built on these coefficients aj, and therefore the definition of memory will determine the rate at which this ages. So this slide looks very similar to the one or two slides back. If ages are absolutely summable and the sum is non-zero, then it's a short memory process. On the contrary, if aj grows like aj decays like j to the negative alpha for some alpha between half and 1, then it has a long memory process. Now, this definition of memory is actually consistent with the one I showed you for Gaussian. If you construct a Gaussian process this way, then the covariance will have. So in Gaussian process setting, be a moving average process. I mean, you can have Gaussian processes which are not necessarily moving average process, but still not. Okay, so in this regime, the clustering is studied in 3 steps. So given E0 epsilon n, we first show that for j running from out of fixed number k and r, and how many of the limit is those events of the on E0 epsilon n. Now, I already told you that I cannot let k go to infinity over here, because the moment I let k go to infinity, this guy will become infinity just by arguments. Okay? So I have k go to infinity. So in the previous slide, 1 to up to k, now I let k go to infinity, and that makes sense of the total cluster size. Okay? So what we showed next is, as k goes to infinity, this goes to some measure on the natural numbers. We call it mu epsilon. And the last question we ask is, what happens to this measure on as epsilon goes to 0? The threshold goes to 0. Let me go over the setup once again. So we have a moving average process. Coefficient is summable, sum is non-zero. Now you can shift by mu and assume mu to be 0 without loss of generality. This assumption is needed for technical reasons, that the characteristic function of than 1 in modulus for all non-zero p, that is its distribution is. And in fact, if you look at the paper of Bahadur and Rangarao, they also essentially needed it, in the sense that the one result was under this assumption and the result was when it's less. Okay? And the answers are different. And we assume without loss of generality, this is possible. You can multiply with the negative sign. Now, this is just for notation. So this is something I call exponential tilting. Okay, so the distribution of Z0 is tilted by theta, and then this is the normalization that makes it a probability measure. So this is called exponential tilting, and S0 is the right end point of the times S0. Okay. Now this is a technical slide. So there exists a tau epsilon, just with the assumption that it has all exponential moments finite, implies that there is a number tau epsilon positive, such that if you tilt by that, you get the mean epsilon by a. Okay? And these are, I mean, we don't have to remember all these. It's just, so these are various tiltings of the original measure of Z0. Okay? So this is a collection of independent random variables whose distribution is obtained by various kinds of, well, simply the partial sum of Gx. And so these notations are just to state the main result. T star follows exponential with parameter tau epsilon by a, dependent on whatever has been defined so far. Un minus and un plus, these are, so if you remember, we constructed the moving average process with Zn's as input. Now what I do is, instead of Zn, I introduce Zn minus, and instead of Zn plus. This I call un minus, this I call un plus. The first result is conditional on E0 epsilon n, this E indicator of E1 epsilon, they converge weakly to V1 epsilon, where Vt epsilon is simply indicator of T star greater than some identity from 0 to V1. The intuition underlying this result is the following. If you condition on E0n, so let's say Sn is simply if you condition on E0n, that is Sn is greater than n epsilon. Now I've assumed them to be 0 mean, mu is 0. So if you condition on this, then Sn minus n epsilon, the overshoot is like an exponential n epsilon. Okay, condition on this guy. So therefore, the idea is, what's happening over here is, the mean of the sample of size n, first n sample points, that exceeds, okay, and the exceedance is like T star. Now I am looking at 2 to n plus 1. Okay, in other words, I am replacing x naught by xn plus 1. Now x naught, that essentially has a limit condition on this, which is the tilted version, and the amount of tilt is chosen in such a way so that you get the mean to be greater than n epsilon. So I'm replacing a tilted random variable by a non-tilted, by a random variable sampled from the original distribution. Okay, so therefore this comparison with the overshoot comes in. Okay, whether the overshoot beats this additional tilt of 1. And so this is, I mean, Vj is like I've shifted by j many points. So that's why the comparison with the tilt and the overshoot. Now, it's easy to understand what happens when, in the case of IID. In the case of IID, Vj epsilon has the following simple form, where Vj epsilon is simply indicated that the overshoot exceeds yi minus yi plus, where now these things are simply IID copies of x naught, and y0 plus y1 plus are IID copies of the tilted sample from the tilted distribution of x naught, such that the tilted mean is epsilon. If you had IID instead of all this moving average process, then this condition on this, you get that x naught, x1, etc. they converge to this. So you just need to check whether the overshoot beats this random variable. That's it.
The notation is a bit confusing. It's minus and plus.
So I mean, minus is what comes in, and plus is what goes out when you move. So finally, we get to the question of what happens to the limiting cluster size as epsilon goes to 0. So limiting cluster size is just, and by the way, from this, it's clear that eventually this beats T star, right? Because this stronger cluster, because this is positive mean. So Vj epsilon is 0 for large J. So sum over Vj epsilon, sum over J, Vj epsilon is 5. So let's call that d epsilon. The right hand side is fine. I mean, I told you the proof for IIT, but that's true. Sorry. The question is, how does d epsilon behave as epsilon goes to 0? Now, as epsilon goes to 0, the E0 epsilon, I won't say it still remains a rare event, but something different happens. I mean, see, we are in a short memory setting, so variance of Sn is like n, right? So this Sn greater than n epsilon, according to the folklore I mentioned, is a large deviation event. But now, if I let epsilon go to 0, it doesn't remain a large deviation event anymore. It becomes a moderate deviation event. Okay? So the answer is d epsilon grows like epsilon to the negative 2. In other words, if you multiply d epsilon by epsilon square, then it has a weak limit. And what's surprising is now the weak limit doesn't depend on anything other than the variance. Okay, so it depends on the distribution only through its variance, and that's kind of unsurprising because what I showed you, it doesn't remain a large division event anymore. It becomes a moderate division. So everything else is as before. It's a standard exponential random variable. Bt is a Brownian motion which is independent of T naught. So we need to understand the invariance. For fixed epsilon, the limiting distribution depends on the law of Z naught. Okay, we this input random variables by tilting them exactly. However, the subsequent limit as epsilon goes to 0 does not. The answer is what I just told you, that this is a large deviation event for fixed epsilon, and hence it's unsurprising that the distribution depends and the limiting law depends on the entire distribution of Z naught. But as epsilon approaches 0, this whole thing becomes a moderate deviation, and hence it depends only through its variance. So let me summarize whatever results we had in short memory. That is, these converge to V1 epsilon, V2 epsilon, which are 0, 1 value random variable, whose distribution depends on that of Z naught, and these are non-degenerate. Each of them is non-degenerate. And as epsilon goes to 0, the total cluster size scales like this. And for Gaussian processes, I didn't show you the results, but Gaussian processes results can be stated just in terms of Fourier. So you can have Gaussian processes which are not necessarily moving average processes. So whatever results I showed, they most sure conditional on this thing. Therefore, the question that we asked a slide back, that doesn't make much sense here, right? Because it will be cluster size will be infinite on shape. So we have to ask a different question. And the reason is which I just told you. Well, I did tell you. So now this variance actually much larger than n. Therefore, deviation of order n is now a moderate deviation. So we studied this regime from a different angle. The question we asked is, how long does this persist? Okay, that is, we look at first time where Ej epsilon n does not occur. By whatever I told you, this goes to infinity almost surely, because for all finite j it occurs eventually. So question is, at what point? Okay, so a few technical assumptions. Okay. Assumption is, I mean, this is easy to check, because I mean, this is essentially where you get it from. For example, if it has a density, and this essentially means that the density is smooth enough, nothing else. The most serious assumption is the first half kappa moments where kappa is given by match with that of the corresponding normal. Now, there are some notations, and there are just notations that define beta, define H, fractional Brownian motion. The fractional Brownian motion is a continuous Gaussian process with this as covariance kernel. And then there's some notations, and then this tau epsilon is the hitting time of the randomly shifted fractional Brownian motion. The result is, if you scale the persistence time in by n to the beta, then conditional on zero epsilon, it's like the limit of tau epsilon. Note over here is the limiting law depends on Z naught only through its variance, which is unsurprising because I've already told you that we are now in the moderate deviation regime. So what we essentially showed is that if you scale time by n to the beta, then Sn, the partial sum, that with some centering and scaling that converges to the fractional problem. Okay. That's hidden in the graph. Okay, so this is exactly what we show, that conditional E0 epsilon, this minus this converges to the shifted fractional Brownian motion. Okay, and on the same event, now this is still true that the partial sum minus n epsilon by some scaling that converges. This is essentially the overshoot. If you remember, earlier the overshoot did not need any scaling, but this needs a scaling. So the idea was to choose beta in such a way such that these two match. Okay, this. So now the moment you have this, you can just simply add them and get that, combine the two convergence. That.
Beta and the first parameter.
Yeah, beta is I skipped it. All depend on alpha, beta and H, they all.
You're in the non-Markovian regime is clearly.
Okay. So this is essentially what we get, and therefore, if you look at the first time this goes, this guy goes below 0 is essentially the first time this guy goes below. Continuous tracking theorem tells us that. Okay. So there's some remarks. So the first remark is like here the persistence time is like epsilon to negative 1 over h, which is much larger than epsilon to the negative 2, and this is obvious that if alpha goes to 1, you are approaching the short memory process where this goes to usual Brownian motion and beta goes to 0. Okay, I'll just tell you why these additional assumptions are needed in the round memory regime. So, how much can I take? 5 more minutes, right? Okay. So there are technical reasons for which we need estimates stronger than Bayesian theorem. Yeah, I'll show you. I'll just go to the main area. So this is I've been talking about tilted distributions. Okay, so I'll just show how the proof goes in that case when x1, x2, etc. are IID with all 5. Okay, and what theta n in such a way such that if you tilt the distribution of x1 by theta n, you get the mean a by n. So the idea is if the mean of x1 becomes a n by n, then the mean of x1 plus x2 plus xn becomes a n. If you sample from this tilted distribution, so that's the idea. And such a theta n exists if probability xn greater than a is positive. Now, to be the tilted distribution, and let xn1 star, xn2 star be IID from Fn. And Sn star is essentially the partial sum of this minus the mean. Okay, so n is now the mean of this random variable. So Sn star is a 0 mean random variable. Now this calculation is primarily for students that they can actually take this as a homework. So I just look at indicator this greater than a. I divide and multiply by this guy. Okay, e to the power theta n x1 e to the theta n, and then I divide by this. The idea is that, and let's change the measure. Okay, Fn this measure has been defined such that this equals this times a constant, and that constant comes out over here. So the goal is now everything except this constant, everything now I define in terms of xni star. The point is now, if I call Sn star is the sum of these things, now Sn star is a zero mean random variable. So this event now becomes a typical event. Earlier it was a, so we essentially changed measures in such a way that we now end up with a typical event as opposed to a rare event. And this expectation can be studied by so Sn star is sum of independent zero mean random variables. So you can use variation type bounds to estimate the error that is incurred in replacing these by the normal random variable, the same mean and variance, with mean zero and same variance. Okay. Now the point is, the long memory calculations. What happened is we needed well, the variation bounds have already been talked about in yesterday's lecture with Krishanga. And he showed there that 1 over root n is the for ideal random variables with finite third moment, 1 over root n is the usual bound. The bound we needed in the long memory regime is sharper than that. And to get sharper bounds, we needed to assume that several more moments match with that absorption, so that we can do a Edgeworth type expansion and get stuff. That's why we had to assume that first kappa moments match with that. Okay, so this is future work. I think I'm already out of time. So yeah, these are the papers on which this talk was based. It's interesting that the short memory paper was published later, although it was submitted earlier. It's because it took a long time to do.
Questions other than short memory papers
Being published later.
Long memory with the referee.
So, in the short memory paper, you fix k and change n.
First fix k,
And then
let
the n go to infinity.
little n go to infinity. Yeah.
So what about make k as a function of n? So what happens?
Yeah, actually, that's a very good question. You can make capital K as a function of n, and I think you can. I mean, any polynomial n. I think you can go even. So the idea is, see, if n is really large, then it's large or exponential. Then these events will occur, right? Not any. So if you let k go smaller than any exponential, then I think you get similar. But we haven't done the calculation. That's just a gut feeling.
Yes. And so one question from me. Bhattacharya Rangarao, they also had a lattice version.
They also had a lattice version. We didn't, yeah, of course. We can use their results and try to get a lattice version, but Bahadur. See, the point is, in our case, it's a bit complicated because if you have exponential IID and from a lattice, then x1 plus the partial sum also belongs to that lattice, right? But in our case, we have these AJs.
So, because the tilting.
Yeah. So, of course, you can still study it. I'm not saying, but it becomes calculations become messier.
Or may not be even because your lattice changes.
Exactly. Yeah.
Okay, let's thank Arijit. No, missing the board in the X. Missing the board in the X. What in the board is it?
White, the white one. Nice.
Everything is okay.
I was in the canteen. But outside
You mix your whole board. I hope so. And if you are not sick, you're not sick.
Yeah.
Oh boy. Let me introduce you. Now we will be one minute introduction. Okay, so our last speaker of the session, Siva Athreya of ISI for last few days, possibly his last talk as from ISI, and also from ICTS. And he will talk about dense random graphs and age vertex dynamics. Look at my mobile, but he will explain.
Thank you. Since I am the last speaker of the academic session, I think we should all thank Anish for organizing this meeting. Okay, so I will discuss broad theme is co-evolution on networks. We work with the graph in which the vertices have processes on them, and the network also is changing with time. And there's a two-way feedback. So let me discuss the model first. Before that, there's joint work with Frank and Hollander and Adrian. So my graph G will have a vertex set depends on n. So you can think of the vertex set as 1 through n. And an edge set that depends, it's a subset of the cross, unordered, undirected graph. So I'll have two parameters, eta and rho. So eta is positive polynomial. So what happens is that each vertex will update its opinion. Let's say it's so assume the opinions to be, let's say, 0, 1. There's two opinions, 0, 1. At rate eta times the number of neighbors. At that time. So that's how the vertices are moving. And the edges will update at rate rho. Each edge in network. Updates at rate rho.
So opinion update means it's with.
I'll explain what it does.
Is this continuous time?
So far, yeah.
But your graphs are discrete. Your graphs are discrete time.
No, I'll couple it.
Oh, this is the.
So what does each at each update what they do? And at each update, the opinion, the vertex adopts an opinion of the next of one of the neighbors. So this is a continuous time model, GMT. So this is a water model on the graph. And what does the edge do? The edge will update itself in the following manner. It will turn itself on or off. Turns on or off. That means it belongs to the network or it's absent from the network. With probabilities that depend whether the ends are, so I just write it as concordant or discordant. Concordant or discordant. This is the model.
And by adopting an opinion means one of the majority opinion or one of the
All of us may do. So we have to say even more precisely uniform.
It's a voter model type. I mean,
It's just water model. Just water model of the network.
that arrow hits with that opinion you take. And the network is pre-given.
Network is starting. Some network you start with. The edges turn on and off depending on whether the edges are concordant. So the probability will be turn on and off depends on the state of the edges. Like it's concordant.
That network related to GN.
Yeah, GN is the network.
So you start with some given edges
That's
at
right.
time zero,
That's right.
and then somehow evolve the edges.
Edges turn on and off. So what the edges can be? Let's draw a simple. I'll draw an example. So each vertex, let's say, has opinion 0 is red and green is 1. That's what each vertex will look like. What do the edges look like? Edges can look like you have 3 possible edges. So either both are red, both are green, or one of them is green, another is red. That's how edge will look like. So the vertices are doing, so I can think of the process of the vertices as, let's say, U1T, UNT as the process of the vertex. This is the vertex process. And my edge set is the
So then the graph is always assumed somehow the graph stays connected. What happens if D is isolated? How do you update the
there's no update. There's no inputs.
It's a continuous time output.
So there's a two-way feedback. The vertices depend on the edges, and the edges depend on the vertices. So, for example, let's do a simpler example. So, let's say rho is 0. So let me put non-negative. If rho is 0, that means the network is static. And it's just a water model on the given graph. That's all. Nothing else. If let's say this is the standard dynamics or random graph. Next day, you can think of it as rho is positive, but the probability of on-off does not depend on the concordance or discordance. So this is a system in which the network is evolving independently of the vertices. That's what it wants to do. But the vertices observe the network at that point in time. So this is like a one-way flow.
And use some other color.
Ah, very good. What I have here is a system of two-way flow. So both the vertices affect the network, and the network affects the vertices. So very little is known about in this setup. I will present one result. I'll discuss some remarks about various types. There are results in both these techniques. Both a model on an random graph is well understood, and even both a model on a dynamically evolving graph with the vertex, with the network autonomously evolves is also understood. If you know how the edge set size remains in a certain proportional to the number of vertices is understood. Okay. So, two things. This two-way feedback is very hard to understand. Except I also have rigged the model in a certain way, so which will, moment I mention the result will be clear. So one observation in the beginning is that the vertices are moving much faster because theta times the number of neighbors. So there are order n vertices changes before an edge changes. So between any two edge changes, your vertices will mix. And that's the key sort of put in the door you can use. So the setup is the following. To answer Apoorva's question first, that we will work in the dense regime. So I'll assume that my E0 is such that the number of edges is of order n squared. I'll start with the dense regime. So almost everybody has an edge. I'll also assume that okay, for this first. Okay. So the key question is, can I describe the dynamics in the n going to infinity? That's the first.
At least along the subsequence. At least along the subsequence.
Yeah, that may be hard as well. I'll tell you what we have.
And the naive. Yeah, so you said these are dense graphs.
Yeah.
The subsequence converges to a graph. Actually, I don't know what.
Yeah, so I'll explain. So what we're able to do is the following, like I said, that the vertices, the opinions mix very quickly. So everybody sees the same fraction density around them. So the vertices see this, so the limiting voter model, and the edges will move like a deterministic flow. That's the first. So the results are the following. So I will not. I will mention the technicalities of the result and explain the full picture. But what we're able to show is that we're able to fully quantify the coupled dynamics. So this is some Grafon learning process XT. I will not go into the details of this, what XT is, as I goes to infinity. The topology is something that I'll describe in a second, towards the end of my talk. But I will tell you exactly two quantities that you can understand. So let's say, so this is the first result. I will not explain, I'll come to it in the end. But let's say the second one I can explain quite well. Suppose phi t is the edge density in the limiting process. If you so the limiting edge density of the graph, how the graph will look.
So GNT is the only vertices 0, 1 is it?
And the edge side, it's a graph.
Also the whole graph.
GNT is this one. The vertex.
Vertex colors, vertex 0, 1s and
It is being concordant or discordant.
So when you say GNT, it's only the graph or also the colors
Also,
and the
everything. The U and the
What do you mean by edge density in images?
So take the number of edges divided by n square.
So these are somehow you're talking about somehow by two-colored graphons or something.
That's right. So I will. That's the theory. I'll put theory on the copy.
Sure. Yeah. But you still say as far as the graphons and the set of graphons, the space of graphons is compact. So every sequence is a converted subsequence, but you are seeing the sequence converges.
Yeah, I haven't told you what the question mark is. Yeah, but broadly.
And there is density in x of t also. Pt is x.
So, but probably think of PP as the limiting edge density of the graph. Probably forget about x is. And let's say Qt is, let's say, the fraction of limiting fraction of, let's say, opinion ones. Okay, so the fraction of those are two things. So I'll explain how these two behave. Then that will give you an idea of how this will behave. So theorem is the following. So what happens is like what you would expect. What do Qs do? If you read appropriately, what will Qs do? Qs will do a Fisher line. So I think this is the eta here. 2 eta Qt 1 minus Qt d. That's what you would expect a Q to do. But of course, since they're coupled here, they're coupled with P. So it will be a P. So the diffusion constant will depend on edge density. And the edge density is a stochastic flow, but so I'll write the drift down. Just slowly. So the stochasticity comes from the Q. And the BPQ, I can write down the BPQ. So BPQ, I'll write this down so we can discuss it for a second. It's SC0 into 1 minus P plus I'll explain what these numbers are in a second. SC1 into P. And then I have a Q squared plus 1 minus Q the whole square. And I have a plus SD0 into 1 minus P minus SD1 into P. And then I have a 2Q and 1. So I'll spend 5 minutes explaining these numbers. This is a drift P. So what is this P now? So when I said this probability, the probability here is P. That's how the edges turn off and on. So that is the edge density. So this probability here, the probability of which it turns concordant discordant depends on 4 things. So one is if they're concordant, it turns off and on with rate SC0 and SC1. If it's discordant, it turns off and on with rates SD0 and SD. You think of 1 as on and 0 as off. So these two people, they will turn off and on at these 2 rates. This one will turn off and on at rate SD0 and SD. That's what the rates here are. And Q is the color density. So what's happening here? If you look at this person right here, moment Q reaches 1, that means the system reaches consensus. Or Q reaches 0. That means the diffusion stays at wherever it's 1 or 0. Then the edge density will be a deterministic flow from that. So that's the consensus model. Once the consensus happens, the edges go off and on in a deterministic way. If you look at when you will have polarization, when you have 2 communities of zeros and ones stuck separately, we don't see that in a stochastic manner. We only see it if PT is 0 and Q is at some number alpha. Then you have 2 communities, the proportions 1s and 0s disconnect completely. That's all. We don't see polarization in this model, unfortunately, and that's because of the tremendous mixing that happens in the edges. So you'll see consensus, that's for sure, because the Fisher right will go consensus. In all simulations, the colors go to 0 over 1. And the edge density is like a deterministic flow.
So why does that happen? Because this your edge vertex changes very fast.
Yeah, vertex between every two edge changes, your vertex equilibrates in some sense. That's what happens.
And your body is dense.
Graph is dense, everywhere. I'm changing, formally speaking, I'm checking in time 1, I'm only changing n edges in my dense graph. So my graph will not change that much.
Would this then also work if it was eta times number of neighbors to some positive power because there's n square in this? So as that
Yes,
grows,
you can, there's a little bit leeway here, but not too much. Okay, so now let me tell you this is a fun part of the picture. I just tell the remarks that will dilute the validity of results. You have to work with, since I'm in the dense graph regime, I have to work with the cut metric or what's called subgraph. So if you want to understand, but there are also colored subgraph. So that theory has to be sort of written out properly. That's already there. You don't have convergence. You don't have reconvergence because the graph. See what is this telling you? This is telling you. I've rigged it in some sense. I've told you that the natural edge density in the graph. So edges of what? Of 3 types: red, red, green, 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 red. So each will have a certain fraction of density in the market. But I've told you that all the edge densities are PT times kind of Q. In some sense, I have sort of converged to the sub-manifold of this whole, subspace of this whole graph space, where the edge densities only see the fraction of colors, not the color at each vertex. Only see the Q, don't see what each thing is. So what happens is that you can't show it in the classical reconvergence. You have to work with what's called the Mayer-Zeng topology.
on what? So topology on what?
It's called Mayer-Zeng topology.
This is the topology on what space?
On the space of, on any metric space, but I use it on space of graph. Is the following: I have 500 convergence. So what happens? What this topology essentially really? I have big convergence, but formally speaking, I have exceptional times where the process will not converge. Formally, as well. That's what this is about. I don't want to go take the detail. I'll come back to this in the last point. Once I write this line, it will immediately become clear. See, this model is doable because you can exploit duality. So the dual for the water model is chorus random walks, and you can immediately show the random walk will mix in the network if you have lots of edges, in order of 1 time, and that's what saves you. So the random walks mix. That means very quickly the colors will homogenize, and you only see Q. You will not see, every vertex will see the same fraction of color. That's the key. That's what you exploit. So at any given point in time, every vertex has order n edges, and random walk will mix in order 1 time. And the duality will give you the idea that this picture is appropriate picture to look at. Of course, the proof is not so straightforward. It is more difficult. So the formal theorem is the following: that this theorem is what I start. So the paths on colored graph space quickly converge to a subspace of. So I write it as just P and Q. By P and Q, I mean that you only see edge density, and everybody sees an homogeneous of colors. That's the thing. So So what are these spaces? Let me just 5 minutes, not 2 minutes.
5 minutes.
So these are what's called a space of graphons, and you work with the cut metric on this space. Of course, you need a colored cut metric. That is what Apoorva doesn't work on this. That's available. And compact metric space. Work is following that we're able to write this metric space. And the generator, it's a nice generator, writes the data down in this metric space. And that's value. We know entirely how the couple dynamics works in the end. Of course, we believe this topology is in it. You must still say the process is convergent or this topology. But this is the correct picture. Limit dynamic looks like edges are flowing like an ODE, and the colors are like an SDE. That's yeah, so thank you.
Questions?
Edge density, but since you mentioned subgraph counts, do you also have to stuff like triangle density?
Yeah, you can add a similar ODE for the coupled ODEs for the
Any subgraph.
any subgraph. It doesn't give much information. The subgraph counts, the edges are a closed form. The subgraphs will go one above. So if it triangles, it depends on the force cycle.
Oh,
It goes up.
edge is close.
Edge is close. Luckily, with edge. That's because of this homogeneity.
So if you look at the set of all subgraphs, you have got them interrelated.
You have infinite SDE.
Yeah.
That is what capital.
And are there only two components? Edge is closed, everything else is there.
On the submanifold, yes. Yeah. If you believe the submanifold picture is this, on submanifold you can factor
And the two connected.
So every subgraph count will be subgraph count of the uncolored guy and the edges. And uncolored.
Color.
Thank you.
And of course, the other natural question is, we have this is the space of two colored graphs and
Yeah.
response. You could ask for three colors.
Yeah,
four
it will go
colors.
through.
Opinions can.
It'll go through.
But then you look at fraction of all the different opinions,
Yes.
the different fractions, and then everything gets more. There are more than 3 types of edges now.
Yeah, so I didn't state it in this fashion, but my the color function is just to take a function from the limiting sense is from 0, 1 to 0. So write it in that sense. I didn't state more than that. Here, I'll assume that everybody is a fraction of
Non-trivial fraction.
not it.
What do you think is sparse case?
In sparse case, I think you can actually work with directly with the graph. I've not done that. I don't see an easy way to handle the sparse case as well. I don't see. You'll have a little harder time, but you'll be able to understand locally what's going on, I guess.
But in the sparse case, do you expect polarization?
You might.
But what? Can you rule out that the sparse will not become dense after a while? Because your edges are changing anyway. Even if you don't have an edge, it may get created, right?
Yeah. So
So
you have to see sparse means what? You can start the extreme one.
So
Let's
you
say irregular graphs.
order in edges.
Yeah, so let's say order n is here, and order n squared is here. Right? Given my network dynamics, I always stay in that regime because I'm only turning off and on at rate 1.
Linear.
I'm not changing the regime. What you're asking is if I change, then I think I change it. But I'm not doing that. I will stay in wherever I am. I'm staying at regime. I'm not go across. So edges will stay where they are. But the question of polarization is interesting. I think it will happen. I think I don't know how to show it.
First of all, if you are in, if you are not within the connectivity regime,
Then
there will be polarization because of the disconnect.
Exactly. Right. You can start with zeros on one side.
The connectivity regime is where.
The moment you have one discordant edge, you'll have a. So I take any dense graph, and I take some. So that means that graph is connected and some uniform distribution zeros and ones.
So independent.
Okay, I should just mention there's a sort of a work with Basu and Sly where they do something similar to this, but they don't study the limiting dynamics. They study, they have different rates and they have rewiring. They don't have on-off.
What is the topology? Can you explain?
The topology
The Mayer thing.
Yeah.
Mayer thing. So Mayer thing, the following. So formally speaking, if you let's say you write the generator at the nth level, the way I've done my thing, I'll get n times some factor plus some factor times formally f prime plus some factor times formally f double. This is what I will get, and plus a big O or 1 over n. This is what is in a generator. So what happens is that if you want to show convergence, if LNs go to L, it never happens because unless this is 0. So this is like a subspace. This is a place where I have this P's and Q's. That is, I see only edge density and I see fraction of colors. That's what the subspace is. So as I'm a process in the subspace where I see only homogeneity colors, this term is 0. So this term vanishes, these parts behave well, and that's what I'm getting here. So what happens in the discrete time level, at discrete time, your process will come into the submanifold, subspace, where you see homogeneity, but quickly get out as well. But when it gets out, it will come back again quickly. But so after you never have deconvergence, because you, at the exceptional time, you always keep going out. But yeah, so this is what you have to show. So you show in exponentially quick time, you land up in this homogenized space, and that's enough to give you this convergence layering form. Without going into detail, that's that. So you will not have deconvergence, you only have FDD. And because you, in the discrete setup, you will show wherever you start in exponentially quick time, you'll come into this subspace where you only see fraction of colors and edges. Not precise in that aspect, that's all.
Okay, so let's thank Shiva and all the speakers of this session. Now it's up to Manish.
So we'll have tea and coffee. So this is the end of the academic part. We will have tea, coffee outside, and then after that, maybe 12:15.
Or 12, let's do it 12 because many people will be coming there.
I am not sure. So as soon as we finish, we come back here.
We come back here for the informal session.
All right.
Now the YouTube live.
বলছি অপূর্ব তোমার কমপ্লিটনেস লাগছে না ম্যাট্রিক্স স্পেস গুলো কন্টিনিউ কনভার্জেন্সের কথা বলছি কমপ্লিটনেস লাগছে না